Okay, so thank you very much. And so basically, this FDP, I believe, is a congregation of several, people, ambitious people interested in research. And the theme of this FDP is revolving around these renewables, microgrid system, and control, and many other advanced technologies. I have just prepared something to share what is based on the control of microgrid with a concept of graph theory. And the topic I have therefore chosen as graph theory based control of a cyber physical microgrid system. Now, what basically I will be discussing in these, allotted time, what is CPS, cyber physical system, and the concept of microgrid and its operating modes and some control objectives and how do you accomplish those, and then how we design a control for microgrid to achieve the different control objectives by employing a very popular technique called graph theory technique. And one such control we design by using this graph theory, a distributed control that I will be presenting. So let me, before I start, let me tell about what is that cyber physical system is now a buzzword across the globe. Basically, we understand cyber physical system as a computer system in which a mechanism is controlled or monitored by computer-based algorithms. That means in a cyber physical system, the physical and software components are deeply intertwined, and the CPS is able to operate on different spatial and temporal scales. Spatial and temporal means in space and time, and exhibit multiple and distinct behavioral modalities and interact with each other in a way that change with the context. That means depending upon the situation, how do you control a physical system by virtue of by employing computer-based algorithms in time and space by interaction with the environment. And some of the examples of cyber physical systems are smart grid systems, autonomous vehicles, inclusive of the automobiles, surface vehicles, underwater vehicles, and many more. And medical monitoring system, that is the health diagnostics, and industrial control systems, robotics systems, and automatic pilot avionics. So these are a couple of examples. There are many. So let us conceptualize the CPS viewpoint of a smart grid. So as you know that any power system, including this microgrid system, comprises of primarily 4 components. These are generation and transmission, distribution, and consumption. In the generation, what you do, we generate electricity by employing different power generators. For example, maybe fossil fuel based, maybe nuclear fission, maybe hydel, or so many things. Now, once you generate all these power source, power, then our next job is to transmit them by virtue of a transmission line. And then comes the distribution, where we step it down and use it for then next level is the consumption. So the consumption is more important in the sense that triggers how to make it more reliable or feasible by employing different techniques. So the transmission moves electricity by a very high voltage infrastructure. Distribution basically steps down the current and spreads out for consumption of industrial, commercial, and residential loads. So therefore, sensing and communication between the grid components, for example, the generation, transmission, distribution, storage, and consumers now can be accomplished in a smart grid by employing the communication and control there, or what we call as by it can be managed by the IT, the information technology. Now, what happens? One of the important concept in the microgrid is basically, like nowadays we are interested to switch on from the IC engine to the electric vehicles. So therefore, this is a very sensible load to the grid, and therefore we need to have something different than ever before. So we want to employ some kind of advanced metering there, what we call as the AMI, advanced metering infrastructure. So those AMI can be collocated and interact with the gateway of a home area network or a business area network. And therefore, the smart meters we can connect with gateways of the home area network, or with the neighboring area network, or with multiple home area networks. So the utility company may leverage a wide area network to connect distributed, neighbor area networks. So basically, what you see the smart grid components like the generation, the transmission, distribution, consumption, and communication, IT, and all of them qualifies that it truly a cyber physical system. Now, when you tell about microgrid, what you understand by that? Microgrids are small scale power networks that are exploited to supply local loads in small geographical spans. And a microgrid typically consists of the power generators, particularly renewables, and the conventional ones as well, the wind turbines, solar photovoltaic arrays, and other renewables. And it has the main component. So like the grid connector or interconnector, that means we have the choice of operating the grid, microgrid independently, or you can connect it to the grid by virtue of the interconnector. You have the operation mode. And the energy storage, like the flywheels or the batteries for short and long-term storage and stabilization. And we have the grid management software and some controllable loads, a robust communication network. If you look at all of them are here in this microgrid, like we have the rooftop solar, we have the different, wind turbines, and then we have the storage here, we have the, we have the switches, and we have the distributed generating sources, we have the plugged in electric vehicles, and we have also the ground connected photovoltaic arrays, and these micro turbines, and many more things. So typically a microgrid may range at the 500 kilowatt to 1500 megawatt. Now these are some of the examples of the distributed generating sources, or what we call as the distributed energy resources. So maybe IC engine could be considered as a non-renewable, micro turbines, fuel cells, or could be renewables like PV, wind, and biomass. And in a microgrid, what typically we do is that we basically create a provision to integrate the renewables to the grid, utility grid, and therefore the different components, if you look at it, like we have the wind power, we have the micro turbine, we have the photovoltaic systems, and all of them are connected by powertronic converters to a point of common coupling, what we call as the microgrid, and then this microgrid is connected to the utility grid back and forth, depending upon your choice by virtue of isolation switch. And then if you look at the concept of the microgrid, so it is basically the addition, like we have the, as I mentioned, the central power plants and the transmission distribution network connecting to the distribution of power to the commercial building, industry, and houses. And in addition to that, in a microgrid, we add the PV photovoltaic power plant, we have the CSP, the plants additionally can be connected, and we can have the power quality devices we can employ here. So basically the microgrid concept with its local and control and power quality support potentially allows for reliable and predictable operation of renewable energy generators, and for scalable addition of new generation and loads. And by virtue of the communication, the information flow can be occurring in both ways. So why we need microgrids? The reason behind choosing microgrid is that we want to curtail the expenditure towards transmission distribution infrastructure in that is happening in a centralized power station, and also facilitating integration of renewables and storage technologies, and also to ensure power quality and reliability, and to adhere to the public policy for effective use of the electricity, and then to make our consumers more smarter than in the connected to the grid today, and also to prevent the blackouts, and therefore we can prohibit the devastations, the blackouts, and then also to ensure the power security, to refrain from being attacked by the terrorists for the cyber attacks. And microgrid provides high quality and reliable power to the consumers, and during disturbances microgrid quickly disconnect from the main grid and operate in an island mode. And by using renewables we can reduce the carbon footprints. So these are some of the benefits of using microgrid. Now, where do apply this microgrid? What are the best applications? Actually, the microgrid can be conceived as the building block for a smart grid, and they are more suitable for remote villages, hospitals, universities, educational institutes, police stations, business and residential buildings, seaboard power systems, military bases, ships, etc. So these are for isolated, or maybe you can connect to the grid as well. And when we talk about the advantages or the concept of the microgrid, but we must look into the control that needs to be done in a microgrid system to ensure a reliable and beneficial operation. For example, the voltage and frequency regulation of the microgrid is necessary both in the grid connected as well as the island mode of operation. And we need to devise a control that will enable us to share the power among the different distributed generating sources participating in the microgrid for sharing coordination. And we need to have a provision, we need to establish a control that facilitates resynchronization of the microgrid to the main grid, and also the power flow control between the microgrid and the main grid, and also to minimize the operational cost of a microgrid, also to handle the transients and restore the desired conditions when switching between different modes, that is the island and grid connected mode occurs. And we know that there are the DC microgrids and AC microgrids are the two popular microgrids, but nevertheless, hybrid microgrids are also a common choice now. Basically, most of the loads, consumer loads, like laptops, smartphones, plasma TVs, they necessitate DC power supply. So therefore, DC is more preferable in these cases. But nevertheless, we also go for AC microgrids. But if you look at this AC and DC microgrid, the synchronization of the AC microgrid and connecting and disconnecting the grid from the main grid is a challenge in case of the AC microgrid than a DC microgrid. And the operating modes of a microgrid, generally there are two modes, grid connected and the isolated mode or islanded mode. For a grid connected mode, we need to have a isolation switch that need to be closed for operating the microgrid in the grid connected mode. And loads are being supplied by both the utility grid and the microgrid in case of the grid connected mode. And we need to maintain the voltage and frequency of the entire system at in accordance with the main grid. And in the islanded grid, on the other hand, the utility grid is not supplying power in these to the connected loads, and all the power is being supplied by the microgrid. And the isolator switch is kept open for this islanded mode, and loads are only supplied by the microgrid. So this is the diagram that depicts about the grid connected mode. You see here, like we have the different DC sources like micro turbine, wind power, and PV. So there are loads like A, B, C. They are connected here with as soon as you connect this isolation switch, so all of these loads A, B, C get or even D directly connected to the utility grid. They get power from the utility grid. But on the other hand, in the islanded grid, what happens when you disconnect the isolation switch, then the loads A, B, C are getting power from the microgrid, but the D, which is the load D, which is connected to the utility grid, doesn't get the power. Now so look at the control problem of microgrids. So therefore, the proper control of the microgrid we need to provide stability and efficient operation. We need to regulate the frequency and voltage of each DG, distributed generation sources, that in the microgrid with a nominal to their nominal values. And then the active and reactive power control between the DG units with the main grid is also accomplished by suitable design of a control. And synchronization of the main grid with the microgrid with the main grid is another control challenge. And energy management and economic optimization of the microgrid. So in a grid connected mode, what happens? The main grid has rotating synchronous generators. Therefore, the group control becomes easier because the frequency reference is there. But in case of islanded mode, we don't have a frequency reference there. So therefore, there is a challenge here how to mimic the kind of high rotating, because there is no inertia in case of the renewable sources like PV or fuel cells, etc. So therefore, we need to mimic the high inertia by employing the some kind of control there. And in the grid connected mode, the main grid provides the voltage support and power quality. But in microgrid, we need to do that by designing a suitable control for providing the voltage support and power quality. And during disturbances, microgrid goes to the island mode to provide power for the local loads. You should make a control how these disturbances can be handled occurring in the microgrid. So, but in addition to this, there are some technical challenges also. Like there is one of the problems with the renewable generation sources connected. Although we claim that we have the facility of connecting the renewables to the microgrid, but like the PV sources, for example, the solar irradiance is intermittent in nature, or the wind velocity is intermittent in nature. So therefore, the high penetration of the solar irradiance may cause instability to the grid, and therefore we need to take care of it. And also, as I mentioned earlier, the low grid inertia for the renewables poses a serious problem for achieving the group control, unlike that happens in case of the fossil fuel or maybe conventional power sources. And also to coordinate among the participating distributed energy resources in the microgrid, how to transfer power, share the power among them. So these are some technical challenges. Therefore, the control objective in microgrid boils down to the voltage and frequency control for both the modes, like grid connected as well as the islanded mode, and proper load sharing of the power among the all the DG sources, and the power flow control between the microgrid and the main grid, and to optimally operate the microgrid. So all these control functions are accomplished by a hierarchical control structure. So this hierarchical control structure is a pyramid structure with a level, different levels. Like we have three levels primarily. One is primary control, secondary control, and tertiary control. So the primary control, which is conceived as the level 0 control, it basically stabilizes the frequency and voltage subsequent to a fault or islanding condition. And this primary control mimics the like as I mentioned, in absence of the rotating mass, or in case of the renewables connected to the microgrid, the primary control mimics the behavior of a synchronous generator in case of the microgrid. And the microgrid basically implements the active power and reactive power based group control in the microgrid. And what the next level is the level 1, that is the secondary control, that basically restores the frequency and voltage deviations that is caused by the primary control. And the secondary control also provides the reference values for the primary control for the voltage and the frequency. And the tertiary control is the highest level control that is responsible for providing the optimal power, for the optimal operating cost for the microgrid. Now, if you so this hierarchical structure of the control for a microgrid, if you look at it, as I mentioned, that we have the primary control, we have the secondary control, we have the tertiary control, and this main grid and microgrid, they are connected by virtue of a tie line. And you see here the primary control takes care of the voltage stability, frequency stability, plug and play capability. Plug and play capability means when you connect several DC sources and loads to a microgrid, and then what happens? Suppose some of the DC source goes wrong. So then in that event, how to synchronize again to go back to the normalcy? That is how quickly we can achieve the tracking or regulation of this voltage and frequency, or stabilize the voltage and frequency despite there is a DC set change, or there could be a change in the load as well. So how do you take care of them? So this is accomplished by virtue of a primary control, and also it takes care of the circulating current, the avoidance of circulating current among the participating distributed generating sources. And the secondary control basically compensates the deviation that is being caused by the primary control, and it basically compensates for the frequency deviation caused by the primary control, both the voltage and frequency. And the tertiary control is important for optimal power operation in both the modes, for the grid connected as well as the islanded mode, and power flow control in the grid tied mode. So these are the different control that is happening in a hierarchical control of a microgrid. Now let us look at the primary control of a microgrid. What happens here? The primary control operates at the fastest time scale and maintains voltage and frequency stability of microgrid subsequent to islanding process when switching from the grid connected mode. So therefore, we need to do something here, how to take care of this stability problem when there is a switching between the grid connected and the island mode. Let us look at these two equations. These are the famous equation of group control. Here, the omega, the frequency of a distributed generating source is governed by this equation, omega equal to omega n minus mp into p, where omega is the generic frequency of the distributed generating source, and omega n is the nominal frequency, and mp the droop coefficient, and p the active power, and E the voltage, and this is the basically the nominal voltage, and Q the reactive power, and Q the droop coefficient. So what is the problem here is that we need to maintain all the DC sources at their nominal frequency and nominal voltage. For that, we need to know that we have to control if you control the active power, you can control the frequency. You can control the reactive power in order to stabilize or regulate the voltage of individual DG. So therefore, we need to maintain these relationships. Like for ith DG, that MP1 P max 1 should be equal to MP2 P max 2 for the second DG, and all of them are maintained at the adhering to these equations. And similarly for the control of the voltage, all of them should abide these relationships. So then what you do here in a microgrid control is that the V0 and I0 are the load conditions from the microgrid. Those are used to calculate the active and reactive power. Then we employ droop control, where the active power is controlled to control the frequency, and reactive power is controlled to control the voltage. And then we get the respective voltage and the frequency. Thereafter, you get the reference required voltage and frequency response to the secondary control. Now, what to do in the secondary control? Our secondary control basically to set the nominal frequency of the ith DG and the nominal voltage of the ith DG in the primary control scheme, such that then we synchronize all the DGs to maintain their voltage outputs at the nominal value, and to maintain all the frequency level at their nominal values. Now, the secondary control can be accomplished either in a centralized control manner or with a distributed control structure. So what happens in the secondary control? This is basically a conventional control technique, where a central controller communicates, or the controller communicates through all the DC sources, and therefore there is a chance that if there is a single point failure, then the reliability is lost. On the other hand, the distributed control structure avoids the need of a central controller and thereby improves this reliability. And this can be implemented on a multi-agent system where each DG an agent. What is multi-agent system is that, if you look at the concept that is a group behavior, cooperative behavior. That means look at the sky in the evening, you will see that a couple of birds are coming back to the nest, are following a pattern of their motion. So if you consider one of them as a leader and rest of them are the followers, so they follow some pattern. So then in that pattern, we mimic in a multi-agent based control. That means each of the bird, if you consider as an agent and their group behavior, how they move, if you mimic that group behavior into a control problem, so that will give a multi-agent system control problem. And in the microgrid control, what you do, we consider each distributed generating sources, for example, photovoltaic system or wind turbine as one of the DC sources, or even you can consider a voltage source inverter connected to the individual DC as also a component, or a filter circuit you can consider as an agent. So each agent has to be controlled by using the concept of multi-agent based control. I will come across this multi-agent system control in the later slides. Now what happens is that each DC communicates with each other via a communication graph, that is called a diagraph in case of a distributed control. So the voltage group control is basically the distributed generating sources control modes are usually implemented using group characteristic technique. The group control method has been referred to as an independent, autonomous and wireless control to eliminate the intercommunication links between the converters. So basically the voltage control is implemented independent fashion. And the secondary control of a microgrid, if you look at it, the secondary control is considered, maybe as I said, that it is a centralized controller that restores the microgrid voltage and frequency and compensate for the deviation that is caused by the primary control. The level of control hierarchy is designed, this level of control design, that is secondary control, is designed to have slower dynamic response than that of a primary control. That justifies decoupled dynamics analysis of the primary and secondary control loops and therefore facilitates their individual designs. So since their dynamics of the control loops are different, one is very fast, the primary control, and then the secondary control is a little slower than that. So therefore we have the opportunity to design the individual level controller to facilitate the hierarchy of control. So if you look at the centralized control, traditionally all these AC microgrid exploit centralized control structures. But what happens is that, as I mentioned earlier, in the centralized control, what happens, the individual distributed generating source like DG1 to DGN are connected to the primary controllers, individual primary controllers, and then what happens, all of them are connected to a main controller. Secondary, this is a centralized control. So what happened, the centralized controller commands globally the gathered system-wide information and require complex and two-way communication network that adversely affects system flexibility and configurability and increases the reliability concern by posing single point failure. So what happens is that if one of the so let us say the centralized controller fails, then the whole system fails because there is only one centralized controller here. So this single point failure means that by the failure of a central controller, the whole control system fails down. But on the other hand, if you use a distributed control where individual controller, you see the primary controller and individual, so there is, you see, only one secondary control, although all of them are individual primary control in the centralized control scheme. But in case of a distributed control, although there are in the previous case we have seen there is only one controller, they are central controller, but here they are distributed across the distributed generating sources. And what you can do, if some of them goes wrong, so remaining also continue to function. So therefore the reliability is more, and this we can implement by virtue of or you can employing by a multi-agent system based control by employing a communication among them, among all the participating distributed generating sources, or with the secondary control, the distributor control. So the third level, the highest level control, as you know, that is the tertiary control. So what it does at the highest level and slowest time scale, it is very, very slow. The tertiary control manages the power flow between the microgrid and the main grid and facilitates an economically optimal operation. So this is the top level of control. As I told that we need to design this secondary control or distributed control, and for that we want to design multi-agent based control. In order to do that, we should know little fundamental about what is graph theory, because as I mentioned you that individual distributed generating sources you consider as an agent, and these agents are communicated by each other by some, let us say, wireless sensor network or something. So in that case, how to design a control by graph theory? So what is basically this graph theory? So this graph theory we basically study to represent the communication behavior or the ability to the ability of this agent to communicate among themselves and to make a decision. So therefore, the communication network interconnecting the different agents in a dynamical system like a microgrid can be modeled as a graph, and with a directed edge corresponding the allowable flow of information between the systems. That means each agent is considered as an agent, and then the connection is the directed connections we call at the edges, and systems are models as nodes in the graph, or these nodes are sometimes called as agents, or what in aggregation we call them multi-agent based dynamical system. And there are few terminologies here. This is a directed graph. A directed graph means a connected diagram. Diagram means the graph connecting all these agents, where every node except one called the root has in degree equal to 1. So here, so the input node, which is the starting node and which that has to be found out. Then we need to, there are some terminology like spanning tree of a graph. A directed tree formed by a graph edges that connects all the nodes of a diagram. This is called a spanning tree. And then a graph means a graph may have a spanning tree if a subset of the edges forms a directed tree, and a graph may have multiple spanning tree. So a graph may have like this. So a directed graph, you look at it in this microgrid system. So what basically we need to represent this as a graph here, or a called diagram. Directed graph is a diagram. Let us consider the DG1 to DGN as the different distributed generating sources, or maybe you can also take the voltage source inverters or the whatever components in the microgrid. Now these distributed generating sources are connected to each other by virtue of some communication link. Now this communication link basically it is there, then this AIJ, let us say ith DG and this is the jth DG. So the strength of the communication is AIJ. If it is no communication, then AIJ is 0. So the then what you basically you can include to represent the agents, you can choose the sensors, you can choose the data acquisition system, controllers, communication equipment, and decision making devices. So as I mentioned that there could be a leader. So when you want to a group behavior, so therefore we choose some of the DG could be a leader and rest could be a follower. And therefore after representing all these distributed generating sources and connecting them by virtue of this communication links, and then translating that to a graph is called basically diagram. Now this graph theory enables us to represent, to come to a control called consensus based control or graph theory based control, in which each diagram or a graph basically we have the nodes, we have the edges, and we have the adjacency matrix. So these three terminologies are very important. And let us say there are n number of nodes and there could be different communications, and this AG is called the adjacency matrix. That is basically formulated depending upon the communication between the different distributed generating sources or different agents. So this typical size for a n node system, it is n cross n. And this AIJ basically if the node receives the information from node Z, so that is 1, or if it is not connected, you can give it a 0. So this AG, if you look at it, the basically look the connectivity, if you can represent in terms of the, so the element, the entries of the matrix AG, what is called the associated adjacency matrix. So that basically either 0 or 1. Now we have another matrix called D matrix. So this D matrix is basically the summation of all the AIG for the nodes, and in the ith row sum of the AG. ith row means, let us say, if you take the first row, the summation is 1 plus 1 equal to 2 here. And then let us say, so therefore the DIs are the entries of this D matrix, or what is called the in degree matrix. And this, so then we are basically interested to come up with a term or a property called LG. So LG is called Laplacian of the graph. So this LG is basically found out by D minus AG, and this capital D is the in degree matrix. So that are the diagonals of all the DI. What I told, the DI means the in degree of node to node. What is the, like the in degree, the node of node is called basically the summation, so that is the diagonal elements. So therefore, from the knowing the LG and knowing the D and AG, you can compute the LG. So this is an example of a graph. Then we find out from this graph, the the connectivity is not there between 1 and 4, the agents 1 and 4, and rest the connections are there, and therefore we can find the diagonal elements and corresponding adjacency matrix, and then you subtract the the D and A, then you get your Laplacian of this graph. So from this graph, we will be able to design a control, multi-agent system control called consensus-based control or consensus-based cooperative control. So we have two control. One is called a regulatory control. The other is a tracking control. In a regulatory control, what happens? Each agent gives the information to control the desired objective. But in a tracking control, what happens? We have only one leader there, and rest are following the leader. So the objective here in case of a consensus-based cooperative control is that to find a distributed control protocol for ith agent that drives all the state to the same constant steady state value. That is, if the state I that should converge to xj, and all of them should be converged to a constant, and that constant is called consensus value. And the control protocols are required to be distributed in that control agent I is only allowed to depend on the state of the agent, that is the depending upon the graph topology. So let us consider there are n nodes in a graph. G has a scalar first order single integrated dynamics, that is xi dot equal to u. You know the xi dot equal to u is a very standard single integrated dynamics, where xi is the ith state and ui is the control input. Now you consider this case that if the dynamics is a single integrated dynamics, we can generate a control protocol for each agent I, as ui is a summation of aij multiplied by xi minus xj. It's not xi, it is xi minus xj. So here this aij, already I told you that is the graph age weights, and basically that comes from the communication between the different distributed generating sources. And this control is called the local voting control, because this takes the information from the locally from the neighboring agents. And please note that all these states are all these states are all the same when like xi dot becomes ui equal to 0. So under certain graph theory connectivity condition, this control, the local voting control, indeed drives all the state to the same consensus value. So our objective is that all the states must be achieving the consensus. That means they must tend to or drive to a same consensus value. We have to find out that. So this concept we utilize to design a multi-agent based control. So for a microgrid, so what you do here, we have two layers here. One is the multi-agent layer, the other is a power system layer. So what is here, like let us say we have the distributed generating sources. Let us say we have the 8 number of DG sources, and this is the power, and this is the this is the microgrid, and this is the communication link you provide there, multi-agent layer. Now what is the characteristic of each agent? That it is a physical entity, unlike a point agent, and it represents electric components, and they communicates each other by a graph, and they are autonomous for decision making. So this is the difference between the point agent and the physical agent. Now we basically now try to design a distributed secondary control by employing this consensus based, graph theory based control or multi-agent system based control. So the control we are going to design is a distributed cooperative control of the microgrid, where the controller requires communication network by which each agent receives the information from its neighboring agents. And it is called cooperative in contrast to the competitive control. That is, all agents act as a group toward a common synchronization goal and follow the cooperative decisions. So therefore, this control, what we can either accomplish this by a regulatory control or by a tracking control. As I mentioned, the regulatory control is one that individual agent work towards achieving the goal. Or on the other hand, in a tracking synchronization problem, we could choose a leader agent and the rest of them will follow the leader agent, and leader agent will track the global objective. So that is possible. So the one we are doing the regulatory control. So here what we do is we represent our, we want to implement this or we want to design a controller which employs multi-agent system concept. Here we have, let us consider the modeling of a microgrid of employing the distributed generating source. So we have a distributed generating source, let us say PV, etc. Connected a voltage source inverter and its accompanied dislink capacitor, and we have the filter circuit, and we have this connector, the line, and the microgrid or point of common coupling. So what you do here, we employ a sensor here, measure the ith DC current and voltage for the 3 phases, and then convert it to DQ frame to make it simple and the time invariant. And then these two quantities, that is the output voltage and output current in the DQ axis are then used to compute the active and reactive powers for the ith DC, and then we filter out the any noise or any kind of outliers here. So by employing a filter, so that will give us the ith DC active power and reactive power. And as I mentioned earlier, our job is to employ secondary voltage control, where we want to maintain the we want to design a droop control such that the frequency of the ith DC will be will be regulated at omega n or the nominal frequency, and similarly the voltage will be maintained at omega ni. So once you do that, so then that gives a reference signal. That reference signal is voltage reference signal is used to design a voltage controller and then a current controller, and accordingly we drive the PWM signals to control this VSI. So this is the power controller that is being designed for the microgrid system. Now this power control, what you do is, our basic objective is that we want to employ the droop control. So therefore we need to design a power calculation block here, where this power calculation that takes the voltage and D and Q axis of ith DC, and the current in the Q axis and D axis of the ith DC, and popular equation of the voltage, the P and Q, P means active power and reactive power, will give you these two values. Then, as I mentioned in my previous slide, by employing the appropriate filter operating at the cutoff frequency omega c, then we get the Pi and Qi and filter out all these outliers or harmonics. So then all these Pi and Qi, now once you obtain, so by controlling Pi you can regulate your omega I to maintain at the with this relationship, droop relationships, that is the nominal frequency minus the droop coefficient into the active power of the ith DC. And similarly, by controlling the reactive power, you can control the voltage of the ith DC. Now, what you do, we know how to implement them in the microgrid system. We make a equivalent DG model of the microgrid. Then the output of the ith DC is represented as the VOI and with a phase angle phi. And this is the line impedance Z theta, and this theta is the impedance angle. And this is the complex power that is being transported to the microgrid from the ith DC. That is, the complex power has two components, P and Q here, and we have the bus voltage V bus with a, let us say, some angle. Let us say for simplicity we consider 0. Now to compute these P and Q, the active and reactive power for the ith DG. So what you do is you use this apparent power, that is S bar equal to V bus into I. So that V bus we know here, and the difference, the I is basically the difference between them, that is VOI minus V bus I by Z. So that gives us PI plus a QI. Now similarly, this active power, reactive power, now you can find out for the IHDG, that if you employ the relationships, so from here we can find out the PI is equals to V bus VOI by Z cos theta minus phi minus V bus square by Z cos theta. Similarly, you can compute QI. So what next you do is that we assume that transmission this line to be inductive in nature. So thereby theta is the impedance angle is 90 degree. So therefore this previous relationship we put theta. So that comes to be Pi equal to this relationship. And Qi becomes this one. So now we assume that this phi is very small. Phi is the angle here, the output of the IFDG. If this angle phi is very small, we can you can approximate sin phi as phi in that relationship here, and cos phi as 1. So that will give us Pi equal to V bus VOI by Z phi, and Qi equal to V bus VOI minus V bus square by Z. Now if you can use this relationship, what you derive here, that your Pi and Qi, Pi and phi, and Pi is related to phi, and Qi is related to VOI. So then, so therefore the controlling P is same as controlling the phi. If you control phi, you can control the frequency, and similarly by controlling Q, you can control the voltage. So then we employ the Drup equations, that VOI as for the ith DG, the output voltage is, let us say, VOI, and the Drup coefficient is KQ, and by controlling the reactive power of the ith DG, you can control the voltage of the ith and maintain at the nominal value of V and I. Similarly, by controlling the active power of the ith DG, and to maintain the frequency at the nominal value V and I. So we can do that by and these Kp and Ki are the Drup coefficients. So now what you do, we have the two Drup control loops here. One is for the frequency, the other is the voltage. So whatever the frequency deviation that is being caused in the primary control, so this deviation, like the P volt to P new, when there is a change, so this whatever change is happening because of this power change, because of the mode change, like standalone mode or grid connected mode. So this deviation is then taken care of by the secondary control. This deviation, like V and mu, and this is nominal frequency it is maintained. And similarly here, the Vn, the nominal frequency, is a new nominal to restore the voltage reference of the voltage. So whatever the deviation is being caused by the primary control from the Q volt to Q new, so therefore this is controlled by the secondary control here. So as soon as so the voltage can be changed, the new voltage is controlled to this nominal voltage. So the secondary control objective here then is to set the nominal voltage for the nominal frequency in the primary Drup control such that, and then synchronize the voltage of all DG units to their nominal values, and then synchronize the frequency of all DG units to their nominal values. So we design a dynamic average consensus based distributed secondary control for the islanded microgrid. So what you do here, the control problem now is very simple. So we use the Drup characteristic, that omega I equal to omega ni minus kp pi, and you differentiate that equation, and then second equation, the voltage equation, also you differentiate. So thereby you get these two equations. That means omega I dot, so with respect to time you differentiate both the frequency and voltage Drup equations. Now what you do is you rearrange these terms, like omega ni dot, then omega I dot take to the right side, and similarly V ni dot takes to the left side, and Vi, and this becomes here. Now here, if you want to get omega ni, you have to integrate it. If you integrate it, you get this relationship. Now for V ni dot, if you integrate, you get these relationships. Now, as I mentioned, that our purpose is to design a multi-agent based control. Please recall that I mentioned about the single integrator dynamics, that is xi dot equal to ui. So here xi's are nothing but your v and omega, v dot and omega dot. And let us consider for the voltage. So xi dot is the va dot and ui for voltage. Similarly for this current. So we need to have two control design, one for the voltage control. So these dynamics are basically the integrated dynamics, and the frequency control input also considered as ui. So we have to design these two control. So as I mentioned, this control that single integrated dynamics for the ith agent, we represent that as xi dot equal to ui, and we have n such agents. Therefore, there are n such equations. And xi stands for the ith agent state of agreement. Either it could be voltage or frequency, and ui the control law. Now, what happens is that knowing your xi, the state, that is either a voltage or a frequency, you can compute the control ui by using the consensus control or local control or voting control that I discussed earlier. So what you do, you want to find out ui equal to xi dot. That can be, ui can be computed as ri dot minus alpha minus xi minus ri, and then this is from this term comes from the graph. Okay, and then where this vi dot is basically the voltage, that is alpha beta and summation of this, where lg the Laplacian of the graph. Now this alpha and beta, what you see here, these are basically the design parameters or controller design parameters, and ri the reference input. What exactly you want to do? Reference means it could be like the nominal frequency or nominal voltage, and xi and like xi the ith agent's output voltage, and this x. So therefore, if you employ this controller employing a graph theory, you can derive what is ui. And for our dynamic average based secondary control for the voltage and frequency control, how to derive? Let us we replace this equation for two loops. One is for the voltage, the other is for the frequency. You did the same. Like when you write ui, I put a v here representing that this control is for the voltage loop, and the xi is replaced by vi, means the ith dg voltage, and v nominal is replaced, ri is replaced by v nominal, and all of them remain the same, that is vj and vi. They constitute the voltage of the ith and jth agents, and therefore only if you can suitably find out these control ui, and other is the ui for frequency, you can accomplish your secondary voltage control and frequency control easily. That means all these outputs, the frequency and the voltage, can be regulated at their nominal values v norm and omega norm. So these equations, these current and these this voltage and frequency. So these two equations are then represented by a control structure. So this control structure gives for the voltage control loop. If you look at it, your ui v equals to vi dot minus alpha this term and this term. So it is here, like we have your ui you want to get. So we have the vj into this component minus vi is here. So it is coming, and then this second term is here. Then alpha is multiplied here, and we have this vi. Then if you integrate it, you get your vni. So that information from the neighboring dg, that is vj, is taken care of here. So this then goes to the primary control. Now the similarly you can represent the second equation, this equation, by virtue of this structure. Now once you do that, then our control is ready. The control is for ith dg, the secondary frequency control with a. Now what happens is that this is the control where we have not taken into account the time delay that is happening in the communication. Let us imagine there is a time delay, because when you send an information through a communication channel, there is always a communication delay, that is let us say tau d. So in order to accommodate that delay in the control, how to get an to compensate this delay, so we represent this delay here. That means if it is a state, T minus tau D, and here is another state, and this is for the second, like the neighboring Ig frequency, T minus tau D. So our control is now modified to accommodate this constant time delay, and this delay to we can define an allowable range or maximum degree of, so that we can the maximum degree of the graph we can take into consideration to define our allowable range of this time delay. That is, we define here tau d could be defined greater than equal to 1 by 2 beta d max, where d max is the maximum degree of the graph. Now we implement this in a microgrid, and what you do, we consider we got 5 number of distributed generating sources, and we consider 5 loads, and we have the transmission line, line 1, line 2, line 3, line 4, and then what you do is we put a communication topology, either a ring topology or a radial topology with these kind of communications like DG1, DG2, DG3, DG4, DG5, and one of them we consider as a leader and the rest could be a follower. And similarly in a radial topology, this is the configuration. Now we take the following specification, like we have 5 DG, that DG1, DG2, DG3, all of them are same. DG4, DG5 are different. Now all of them are required to maintain at a reference value of voltage at 380 volt, and then all of them should be maintained at a frequency 50 hertz, and these are the coefficients for the control we have chosen. For Kp, Kq, that is the droop coefficient, these are the values, and for the line impedance, this is the load, RL load, and this is the RF and the filter circuit, like R, LF and CF, and these are for the voltage loop, what is the droop coefficient, and then these are the current loop. So these are the corresponding values. So these are taken from a paper to establish that the reality, the real system, to mimic a real system. Now the specification continues with the the line impedances. The line impedances for the 4 line, we consider them RL loads, and the line 1, we have line 1 and line 2, line 3, line 4, the corresponding values of R and L are given here, the resistance and inductance values, and the loads are chosen as RL load for load 1, load 2, load 3, load 4, load 5. These all these specifications are taken from this paper by Pogaku et al. So then we simulate, and after we simulate our controller that I discussed, then we compare their case 1, when we have a communication topology, we have chosen a ring topology, then what happens? Like you see, we have this graph shows that there are 5 digits, and at 1.5 second we switch on the secondary control that we design, and we see that as soon as we switch on, all of these DC voltages are maintained, are stabilized at 380 volt. But what happens at at 2.5 second, we increase load 1, and therefore there is a deviation or there is a disturbance here. They all deviate from the nominal value, but after some time, let us say 0.023 here, so they go to their nominal values. Now same thing again at t equal to 3.5 second. Let us imagine the load 3 is disconnected. So if the load 3 is disconnected at 3.5, still you see they are coming to their normal voltage and normal frequency, and these are the corresponding voltage, the power, active power and reactive power characteristics. Now you take a radial topology. You see when the controller is implemented, even when you change the topology from ring to radial, and do the same kind of deviation in the load or arrangement in the load change, etc., but the controller is good enough to enable all the DG to maintain their respective nominal values of the voltage at 380 volt and the frequency at 50 hertz quickly. So that means the controller exhibits efficient performance and synchronizes the voltage and frequency to their nominal values, and these are the corresponding active power and reactive power responses. Now we compare our result with some of the earlier work by Bidyadhar et al. And you could see here that the proposed one is a blue line for the voltage regulation, and the dotted line is for the frequency regulation problem. Now we see here that the proposed controller, the one I am presenting here, exhibits a better restoration when there is a disturbance in the system like a load change, etc. As you see here, compared to the red line, you see the blue ones, the proposed one is certainly quick suppression of the deviations. And these are the power, deviations or swings in case of the earlier work, and ours there is no deviation much in case of the active power. Now we also study the effect of communication latency. So communication latency means when you send a signal and receive the signal, so there is a time lag or time delay, that is called communication latency. So in order to verify the effectiveness of the proposed controller, what we do is we choose the different values of this communication latency, that is tau d equal to 0.1 second, tau d equal to 1 second, and tau d equal to 2 seconds. And you see when we choose a very low communication latency, that is 0.1 second, then what you see that you see here the voltage and the frequency curve, the curves, they are here you see here. And in case of the latency increases, you see there is a little deviation here. And again, if you still increase the latency, you see there is more deviation in the voltage. So therefore, there are two things we observe, that if the communication latency increases, the convergence time to converge, it faster, but here it takes more time to converge to the nominal value. And also there are some oscillations here in this around these nominal values in case of higher latency. So the scalability also we studied with respect to our controller. Our controller is not only we implemented in a small system, but also we applied the same in a modified IEEE 39 bus system taken from the reference 25 by Zhao et al. And we could see that the proposed controller also maintains the regulation of the voltage and frequency to their nominal values at the different time instant when the loads are changed or the kind of disturbance or happen. So the next what you do is we also study the plug and play operation. That means when at 2 seconds we have connected the controller, and 3 seconds you disconnect a DG. Let us say DG5 is disconnected at 3 seconds. As soon as you disconnect it, and then what happened, there is some disturbance or transient occurs. But again we connect this DG at t equal to 4 seconds. So we could notice that even though there is a small disturbance or oscillation because of these transients or the load, the disconnection and connection, but because of this controller, they are coming to the normalcy very quickly. And the proposed control also enables the restoration of the nominal frequency quickly. And these are the corresponding active power and reactive power characteristics when the DG5 is connected and disconnected. These are the different behavior of the power transfer. So the proposed control scheme, from this graph we see the controller what we have designed exhibits a robust restoration performance with small transient and disconnection and reconnection points. So therefore this particular control enables the plug and play operation. That means you can accommodate the different time of switching the distributed generating sources to the microgrid. Now the summary of the work that I am presenting here, we proposed a dynamic average consensus based distributed control for both frequency and voltage, and the results show that the proposed scheme restores the voltage and frequency effectively. We change in communication topology. When you change the radial to ring, then the same kind of restoration achieved, and also the link delay or the communication latency is taken care of. And we can also visualize that the scheme is also applicable to higher system like IEEE 39 bus system. And the control scheme also supports the plug and play feature. That means when a DG is connected or disconnected, we can still use the same controller to restore the frequency of individual digi to their normal nominal values. And therefore, we can accomplish this by a simple communication network. And the performance of our controller is also compared with an earlier controller, and we could see that our controller exhibits faster synchronization, and also little oscillations are there. But one problem with the current controller what you are proposing is that it doesn't take care of the how fast the convergence. You need to ensure that if you want to specify my controller should achieve this, then we need to redesign something. So in order to do that, we have also redesigned this asymptotic based controller, in which we accommodate that how fast we can achieve this, this for sensitive load, how quickly these deviations, because I mentioned that it happens that 0.22 second or 0.23 second. But if somebody wants that it should happen 0.1 second, so what change you need to do? So for that you need to define this time, so that asymptotic behavior must be defined for quick convergence for sensitive loads. Also here we have I have not presented that there could be some packet dropouts. So how to take care of those packet dropouts in the communication link? So all these things can also be taken. So there are few things still can be studied. The interested researchers can take it up, and this very interesting additions can be made. And I invite some questions from the audience. With this, I formally concluded my presentation, inviting questions from the participants. And these are some of the references you see. Like this one is these are the people like Bidram, Lewis, etc. They work on this area, and these are some of the work. And this industrial electronics by Guerrero, and there are other like Vasco and this Bidram. And we have a couple of papers published in this like IT Smart Grid and all. So these are also, you can find it somewhere in the IEEE Explorer. So some quick questions, please. Yes, please. Hello.
Participants, please unmute your mic and you can ask the question.
Okay. So if you have no question now, you can also mail me later. If you can think of.
Yes,
okay.
Kavale, any question from the participants?
No, sir, I cannot see any questions. They are just writing, thank you, sir, for the informative session, and the feedbacks are there, but questions are not there.
It's okay. Sir, hopefully the participants have no question. Thank you, sir, for complete overview of the microgrid with the control strategy. Really, sir, I was completely attending this class. I got the idea also, few things, how the active, reactive power control, voltage frequency. Hopefully, it is very much useful for the participants. And if the participants need any kind of support, they can communicate through mail also. And sir will share the PPT. Once sir will share the PPT, I will share among all the participants. And
Okay.
thank you. Thank you,
Thank
sir,
you
very
very
much.
much.
Sir,
Thank
at
you.
least
Thank you.
you have given the time for us. That is
Thank
our
you.
privilege. Thank you, sir.
Thank you very much. Thank you.